Okay. What about 31? Okay. So let's look at 31 on page 631. 3a minus b minus 4c equals 3. 2a minus b plus 2c equals negative 8. And a plus 2b minus 3c equals 9. I know you can see, I'm working on it. Okay. So we're asked to use Gauss-Jordan on the system and determine A, B, and C, basically the triple that represents the solution of the system. I noticed that the system is in the correct order, A below A, B below B, C below C, the equal symbol, and the free terms. So this is in the correct order. What do I have to do first? Present the augmented matrix. Very good. So here's the augmented matrix. Can anyone dictate by rows? By rows. And then 2, negative 1, 2, and negative 8. And then 1, 2, negative 3, and 9. Good. So now remember, our first step is to have a 1 in the upper left corner. Is there anything I could do to get that done? Say it again. And multiplying by negative 2 will give me a negative 6. So it will not give me a 1. Say it again. Yes. So row 1 becomes row 3, and row 3 becomes row 1. Excellent. So 1, 2, negative 3, 9. 2, negative 1, 2, negative 8, and 3, negative 1, negative 4, 3. That is the best option for now. Yes. What is the next step? So for now, we have the 1. That's achieved. Corresponding to this 1, or using this 1, we will have to eliminate the 2 and the 3. So which row we are going to make use of to eliminate the 2 and the 3? The first row, obviously. We will multiply by something to add it to row 2, and by something else, or sometimes the same, to add it to row 3. Yes, so the first one will be negative 2, and the second one will be negative 3. So I caution you that the book does not show these two steps together. Okay? I highly recommend it because otherwise you may lose track of what you're doing. So it could be potentially more difficult and much longer. So I recommend doing these two steps at the same time. Okay, perfect. Next step. Which row do I have to copy because I'm using it? And if I'm using it, it cannot change. I either use it and it doesn't change, or I don't use it and it changes. It cannot be both. The first row needs to be copied. 1, 2, negative 3, 9. Very good. So now let's do this together. 1 times negative 2 plus 2. 0. 2 times negative 2 minus 1. You agree with negative 5? So it's negative 4 minus 1. So negative 3 times negative 2 plus 2. Perfect. 9 times 2. Negative 18 minus 8. Ugly for now. We'll see what happens next. 1 times negative 3 plus 3. One times negative 3 plus 3. Perfect. 2 times negative 3 minus 1. Ugly. So negative 3 times negative 3. Negative 3 times negative 3. 9 minus 4. 9 times negative 3. Negative 27 plus 3. Yep. Awful. I have no choice. What is our next step? Divide row 2 by negative 5. Super ugly. Let's make sure that I copy the system correctly. I don't know the answer. I'm just saying. So just making sure. 3 negative b minus 4, yes. 2 negative 1, yes. And a minus plus b minus c, yes, correct. So now I'm checking our numbers again. So it was 1, 2, negative 3, 9, correct. 2, negative 1, 2, negative 8. 3, negative 1, negative 4, 3. Yep. Okay, so one more time. Negative 2, yes. Negative 4 minus 1. And then 6 plus 2, yes. Negative 8, yes, that's correct. Then 0. And then 6, negative 7, that's correct. 9, 5. And 27 plus 3. Yeah. Okay, so that it is what it is. Good. I copy the first row. And I divide the second row and I get 0. Then I get 1. Then I get negative 8 fifths. And then I get 26 fifths. And 0, negative 7, 5, and negative 4 will stay. Is this okay so far? Yes? Is that okay? Good. So we accomplished all this, as well as this. Now we have to make the use of 1 to eliminate these. Which row we have to use right now? Yes, we are using row 2, of course. It's step 2. I have to use row 2. What we multiply row 2 by to eliminate the 2 at the top? Yes. What we multiply row 2 by to eliminate the negative 7? Great job. Let's continue. Which row do I have to copy because it's guaranteed will not change right now? Row 2, of course, is the one I use. 0, 1, negative 8 fifths, 26 fifths. Of course, on 1 and 0 will not get damaged. Otherwise, I'm going backwards instead of forward. Okay, let's do this together. 1 times negative 2 plus 2. Good. Careful now. Negative 8 fifths times negative 2 over 1 is 16 fifths. 16 fifths has to be added to negative 3. 15, 16 minus 15, 1 fifth. Now careful at the next step, because when I multiply these two, I get negative 52 fifths plus 9. 45, so this is negative 7 fifths. So with these fractions, you have to be careful. Should we do this row one more time? Or is it clear? So it was 1 times negative 2 plus 2, and this was positive 16 fifths, but minus 3, and I got 1 fifth. And when I multiply these two, I get negative 52 fifths, and then plus 9. 5 times 9 is 45. Negative 52 plus 45 is negative 7. So that's how I get the negative 7 fifths. Okay, now 1 times 7 minus 7 is 0. 7 times negative 8 over 5th. Negative 56 fifths, but plus 5. And that's 25. So negative 56 plus 25 divided by 5. So I got negative 31. Is that correct? And the last one. I'm checking my numbers. I hope I'm okay. So we'll see in a moment when we check. So 2 and 4, so 182 over 5 minus 24, but it needs to be multiplied by 5. So 182 minus, I think is 120 divided by 5. So I get 60. 2 over 5. What have we accomplished? A lot. Where are we now? Where are we from all these remaining ones? Where am I now? Where am I looking now? Right here. So what do I have to get here? So what should I do to both sides or to this row to get a 1 here? Multiply both sides by negative. Yes. So here we have to multiply in the next step. We multiply row 3 by negative 5 over 31. Okay, so when I multiply 62 over 5 by negative 5 over 31, I like it because I get negative 2. So now, since we obtained the 1, all we want is to get the 0 here and the 0 here. This is the last step, so we know exactly which row we multiply. And we know it's row 3. What should we multiply row 3 by to eliminate 1/5? Of course, negative 1/5. What should we multiply the last row to add to negative 8/5 and get 0? Very good. Awesome. Great job. Good. Which row I copy? Because it will not change. Right. Good. So 1 times negative 1/5 plus 1/5. Answer. Perfect. Negative 2 times negative 1/5 will be 2/5. So negative 7/5 plus 2/5 is negative 5/5, which is negative . Last step. 1 times 8/5 minus 8/5. Negative 2 times 8/5 is negative 16/5 plus 26 over 5 is 10 over 5, which is... However, do I know that this is correct? No, I don't. So what is the triple that you hope is the solution? I hope that too. Trust me. So what do we hope the solution is? Very good. So we go back with a negative 1, 2, negative 2. Negative 1, 2, negative 2, negative 1, 2, negative 2, negative 1, 2, negative 2. I'm holding my breath. Okay. So negative 3 minus 2 is negative 5. Negative 5 plus 8. Okay. Promising. Negative 2 minus 2 is negative 4. Minus 4, negative 8. Promising. Negative 1 plus 4 is 3. 3 plus 6 is 9. Unbelievable, but true. Yes. Any questions? Your test will not, this problem tested kind of endurance, right? And didn't really test the method. So I'll make sure that your problem will not test endurance. It will just test the method. So that was 6.1, and we have one more section to go through. So please tell me what you would like me to do. You like to continue and finish up last section? Or you want to go back to another problem? What would you like to do? Let's finish up. So you have time, we have time to review thoroughly. Okay. Last section, it's 8.1. Yes, please. Absolutely. I know you're happy now. The answer is yes, absolutely. I'm happy we have time to review for this test, at least a session, maybe even 2, and then review quietly and peacefully and patiently for the final. Is that okay?
Yeah.
Okay. This is a piece of cake. This last section has a little bit of information that we probably haven't seen before, but nothing difficult. I think you're not going to find it difficult. I hope not. So it's about sequences. I'm not going to define sequences first. I need 2 pieces of information here before we continue. Okay. So before we even talk about this, I have a couple of preliminary pieces of information. And here is the first one. It's called factorial notation. And you'll see how is this connected to the topic of this last section. So what does this mean? For example, if we talk about 4 factorial, this is just an example, 4 factorial. This means the product of the first 4 numbers. 4 times 3 times 2 times 1. 4 times 3 is 12, 12 times 2 is 24. What about 2 factorial? 2 factorial is 2 times 1, which is 2. What about 1 factorial? What do you think this would be? Just 1. What about 0 factorial? You may not like this, but 0 factorial is also 1. By convention, 1 factorial and 0 factorial equal the same number. So what is the general notation? Here's the general notation. It's n factorial, which means this. N times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. And this is applicable, this definition is applicable to any factorial. So if I have 10 factorial, I would have 10 times 9 times 8 times 7 times dot 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 times 3 times 2 times 1. Okay, now let's suppose we want to simplify an expression with factorial notation. Something like n factorial divided by, let's say, n plus 2 factorial. So as you see, you can't get in parentheses to replace or simplify anything. Which of these 2 will be a longer product, you think? The n factorial or the n plus 2, n plus second, we can say. Which one is bigger? The numerator or the denominator? The denominator, because it has n plus 2. So let's leave the numerator alone. And please tell me, what will you write for the denominator? Let's say we want to expand n plus 2 factorial. Where do you start? All right, we have to start with whatever we have. If I have 4, I start with 4. If I have 10, I start with 10. If I have n plus 2, I have to start with n plus 2. That's the definition. Which one is the next factor? What do you think? If this is 4, what will be the next one? Yeah, so how do we get the next one? If I have n plus 2, what will be the next one? Of course. What will be the next one? N. What will be the next one? Right, but I want to stop at n. How come? How come that I don't continue? Because now I see something very important. What do I see? Yes, I see that these two go away, and the simplified form is 1 over n plus 2 times n plus 1. And it's done. So I simplify the expression that had initially factorial notation into a simple rational expression with 2 factors in the denominator, and we will not distribute them. This is it. That's the final answer. Let's look at another situation. Let's say I have 22 factorial divided by 16 factorial. This time, and I'd like to show you how to find this in the graphing calculator as well. This time I have a numerical expression with factorial. Okay, which one of these top and bottom is bigger? Do you think that 22 factorial will be larger as a product, or 16 will be larger? Which one? Of course, that's my starting point, and I will leave 16 alone. So what do you think how the top will change into? Indeed 22 times, indeed 21 times, indeed times 20 times 19 times 18 times 17, 16 factorial. And I can simplify 16 factorial with 16 factorial, and I have to multiply this. This is going to be a big number. Let's multiply those, and that's the answer. We have another option here. So 22 times 21 times 20 times 19 times 18 and times 17. And the answer is 53,721,360. 1,360. Okay. So here's another way. From the very beginning, go to math, go to probabilities, across to probabilities, and as you see, there is the symbol of factorial. However, we have to put in 22 first. So parentheses, 22, go to math, go to probabilities, copy number 4, close the parenthesis, divide by, in parentheses, 16, and then go back to math, copy number 4 from probabilities, close the parenthesis, and when I hit enter, what should I get? Right. If not, something is wrong. So there is a way of simplifying the numerical ones, but if we don't understand to simplify the numerical ones, we will not be able to simplify the ones with variables. Okay, how do we feel about the factorial notation? How do we feel about the factorial notation? Should we find another example? Okay, here's another example. Page 752. Let's look at 26, which is 20 factorial over 2 factorial times 18 factorial. And also let's look at 28 on the same page, which is 2n plus 1 factorial divided by 2n factorial. Okay. Yes, with the numerical one, you can punch it in the graphing calculator. However, the calculator has a limited space. So if any of the top or bottom exceeds the calculator memory, you're not going to get an answer. You're going to get an error. So it's still valuable, a valuable tool to be able to simplify these expressions before you put them in the calculator. And the first one is not such a big deal, right? Which one of the 20 and 18 is bigger? 20. So then this is nothing else but 2, so I'm going to copy 2. I'm going to copy 18 factorial because we know that 2 factorial is 2 times 1. And the numerator is 20 factorial. What do I have to write? For 20, instead of 20 factorial, I will write 20 times 19 times 18 factorial. So I stop at 18 factorial only because I see that this goes away. Of course, I will simplify by 2, and the answer is 10 times 19, which is 190. And that's it. Now, with the second one, I can plug it in, the calculator. So now what? I always ask myself which one is bigger. It is the top or the bottom? Right. Not too much bigger, but still bigger. So how will I write the numerator? And I will not disturb the denominator. Indeed, 2n plus 1 times 2n factorial, because these two go away, and the answer is very nice, just 2n plus 1. Is this clear? Is the idea clear on how to manipulate these factorials and how to simplify them? Yes? Okay, there is another preliminary before we talk about sequences, and that is the summation notation, also called the sigma notation. So this is the summation notation or sigma notation. So this letter is the Greek letter S, sum. It stands for sum. So you could say, okay, if you're talking about the sum, why don't you use this? Isn't this good enough? This is good. But we prefer that notation because of convenience of writing something on it, and I'll explain in a minute what it is. So this is nothing else but S, the sum. But we prefer the Greek sum, the Greek sigma, in other words, the Greek letter S, which is sigma. And this is it. Okay, why? So first let's discuss when we use it, and then I'll tell you all about it. So let's suppose I want to add 1 to 2 to 3 plus dot dot dot, exactly 3 dots, plus 10. Since the operation symbol between each sequence of 2 terms is the sum, we're going to use the summation notation, or sigma. What is the first number, which is also called here? It's 1. This is the lower limit. The lower limit. So we use normally indexes. So I, J, or K. You can use any index you like, but this is normally, these are the usual indices, I, J, or K. What does this mean? Okay, from I equals 1, from the first term, when I is 2, I get the second term. When I is 3, I get the third term. Till what? What is the upper limit? How far do I go? From I equals 1 till 10. From I. So 10 is the upper limit of the index. And now you'll say, this is not that big of a deal. Why do you have to use this sophisticated notation for these 10 simple numbers? It's because it's way more convenient, and you'll see why. Okay, now I'm going to give you the sigma notation for something, and I would like you to expand it and tell me what this is. So I'm going to say the sum from I equals 3 to 6 from I plus 1 squared. First of all, how many terms will this notation or sigma have? You will have term when I is 3. You will have a term when I is 4. You will have a term when I is 5. And you will have a term when I is 6. 4 terms. Can anyone give us those 4 terms? 1, 2, 3, 4. Bless you. So when I is 1, do not calculate anything. I want everyone to see what we're doing here. When I is 3, what will be the first term?
16.
Right. So let's write it like this first for everyone to see. And then, yes, it is 16. The next one will be 4 plus 1 squared. The next one will be 5 plus 1 squared. And the last one will be 6 plus 1 squared. And of course, indeed, 4 squared will be 16. 5 squared will be 25. 6 squared will be 36. And 49. And now I can add them. So I get 52, and I get here 74. And I think I got 126. So whenever we want to condense something and explain it quickly or perform operations with it, we prefer this notation versus this. Well, see, this sum had only 4 terms. But what if I say this? Let's say the sum from j equals 1 through n from j squared. This one doesn't have 4 terms. How many terms does it have? It has n terms. So it will have 1 plus 2 squared plus 3 squared plus dot 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 plus n squared. So this is a much easier situation. And then we have formulas. You do not have to memorize them, but I want to show you one. And you will be hopefully amazed. And there are a couple of properties of, I'll present a couple of properties of the sigma notation. Okay, so let's say we want to add the sum of squares of numbers. Let's say from j equals 1 to which number would you prefer? Pick a number. If you pick 2, I will just add 1 squared plus 2 squared, which is very easy. If you pick 3, I will add 1 squared to 2 squared to 3 squared, very easy. But if you, for example, if you pick 1,000, then it will take me 3 days. But there is a very nice formula for this, which is n n plus 1 divided by 2, where in our case n is 1,000. And it will take me 3 seconds to tell you 1,000 times 1,001. So this is 500. So when I multiply 1001 by 500, I have 500500, and I'm done. It's 500,500. Why? Because I know the sum of all the numbers squared starting with 1 till anything you want. And the formula is right there. So if at any point in time you want to say, let me add the squares of the first 39 numbers, you will then write from j equals 1 to 39, and you will put here 39, and then times 40 divided by 2, you perform the calculations, and you have the answer. So the summation notation is very powerful. Okay, so let me give you 2 properties. There are 3, but we'll condense them. So let's say we have the sum from I equals 1 through n from I squared plus, let's say, I cubed. These are 2 separate terms, right? I squared is one thing, I cubed is something else, and you cannot combine them. They are not like terms. Well, the sigma notation allows us to do this. From I equals 1 through n from I squared plus the sum from I equals 1 through n from I cubed. So if we're applying the summation notation to a sum of generic terms, we can separate the sum. This is a major property. Please don't say we're distributing the summation notation. We're not distributing the summation notation. Now, if we have minus here, what do you think happens between these 2 terms? If we have subtraction of I squared minus I cubed, what do you think? Right. So that's why I said I'm condensing those 2 properties into one. So if you have the sum of 2 generic terms, then you can split it into 2 summation notations. Okay, here's one more property, and then you'll see what we do with this. So here's another property. Let's say the sum from I equals 1 through n from a constant, I'll pick I squared. What does this mean? It means the constant times 1 squared plus the constant times 2 plus the constant times 2 squared plus the constant times 3 squared plus the constant times 4 squared plus the constant times 5 squared plus the constant times n squared. So what do you think we're going to do if it's a constant in front of the generic term or general term? What do you think? Just a wild guess. We can factor out the constant from all those terms and write C times the summation or the sigma notation from I equals 1 through n from I squared. So if there is a constant, we can pull it in front. So let's look at a couple of examples here before we continue. Okay, I don't see any. I want to make up. Here it is. So let's say the sum from k equals 1 through 4 from 2k minus 1 times k plus 2. First of all, I'm going to ask you how many terms does this summation notation have? And you will say the summation notation has exactly 4 terms. When k is 1, when k is 2, when k is 3, and when k is 4. That's it. Can anyone without calculations give us those 4 terms? You could say, and I will have to agree with you, Why don't we distribute? Okay, it's possible. 2k times k is 2k squared. 4k minus a k plus 3k and minus 2. Okay. Now, I will say the sum from 2k squared plus the sum from 3k minus the sum of 2 from k equals 1 through 4, from k equals 1 through 4, from k equals 1 through 4. What did I just do? I applied the first property that says the sum of three terms can be presented as the sum of the summation notations. I'm not distributing, I'm just thinking. The sum of three terms is the sum of the first plus the sum of the second plus the sum of the third. Okay. Here I see a constant. I can put it in front. So this is 2, the sum from k squared. The next one is 3, the sum of k. And the last one is negative 2, the sum of exactly. Of course, all of them from 1 to 4. Exactly. Okay, now 2 and in parentheses, what will you give me? And how many terms again? You will give 1 squared, you will give plus 2 squared, plus 3 squared, plus 4 squared. And this is this. Then you will say plus 3, and in parentheses, what will you write? When k is 1, 1, plus when k is 2, 2, plus 3, and plus 4, minus. So all this is this. Minus 2, and what will you write in parentheses? When k is 1, 1, plus when k is 2, 1, plus when k is 3, 1, plus when k is 4, 1. Questions? So far we haven't finished. Okay, so then final stage in which we perform all these calculations. So how much is 1 squared? So this is 1 plus 4 plus 9 plus 16. So let's write that. So 2, 1 plus 4 plus 9 plus 16 plus 3. So this is 10, isn't it? 5 and 5, so 30, minus 2 times 4, which is 8. So let's see what we get. So this is 10 plus 20 is 30. 30 times 2 is 60. And plus 22, 82. Questions?